Hey everyone, so today let's go over LeetCode question 145, which is binary tree post-order traversal. Now this is somewhat similar to our last video, which is on pre-order traversal, but this is going to be a little bit reversed, right? So given the root of a binary tree, we want to return the post-order traversal of its nodes values. So we have some examples here. So given this tree, we want to return everything on the left side first, and then everything on the right side, and then the root itself. So it basically goes left subtree, right subtree, and then the root that you're looking at. And we'll go over an example in a little bit to kind of define what post-order traversal means. But in this example, like you have this tree, one with the right subchild of 2 with the left child of 3. So what we're gonna do is we want to prioritize outputting the left subtree first. So in this example, there's no left subtree. So now we look at the right subtree, which has 2, right? So 2 has a left child of 3. So remember, we're prioritizing the left subtree. So since 2 has a left child of 3, we output 3 because 3 is the bottom of the tree here, and 2 doesn't have a right child, so we then output 2, and then we kind of bubble our way back up and finally output 1 here. So this question is just like the last one, is recursively pretty easy. Again, we'll do that in a future video, but let's try to do this iteratively, which is a little more challenging. So I'm gonna try to split this video into 2 parts. So the first part, which is this video, we're gonna go over my solution, which I'll be honest, like the iterative solution didn't come too naturally to me. I also haven't done LeetCode in a while, so I'm a little bit, still like catching up, still reviewing some concepts and some thinking patterns. But let's go over the way I did it today, and then in another video in part 2, we'll go over one of the ideal solutions that they have in the discuss section. So yeah, let's get started just kind of brainstorming and trying to understand the question better. Let's go over a simple example starting off just to see if we can get into the mindset of thinking about this. Like I said, this is a bit of a tricky question. So this approach is going to be somewhat similar to the approach that we took for the in-order traversal, the last video. So I'll link the video in the comment box below. So let me open up Sketchboard here. Let me go here. We don't need to copy and paste the problem because it's pretty straightforward. So, okay. So first of all, let's look at what is post, let me zoom in. Oops. What is post order traversal? So post order traversal is essentially, like I mentioned, we want to visit all nodes on the left side in this order, and then visit all nodes on the right side, and then we basically visit the root node. And by visit, I mean essentially output as the result. Okay, so it goes left, right, and then root. So again, in this example, we kind of already went over it. Let's go like maybe a little bit of a more complex example just to kind of give you an idea of how this works. Let me move this down. Where is the circle? There's my lovely circle. Okay, let's say this is node 1, and let's have maybe something like this, something that kind of goes into both sides of this this root node here. I'm gonna do the freehand. Sorry, it's not like a perfect line, but hopefully it kind of suits, get the intention of this. Let's call this 2, and then let's make a right child here. Okay, sweet. That should be good. Awesome. And again, let's make this 4 here. Awesome. Okay. So in this case, what would be the result of a post-order traversal here? So remember, we're going left, right, and then the root. So in this case, let's start at 1. We see that 1 has a left child, right, or a left subtree. So let's start going down the left subtree. So we see 2. Now you ask the same question again. Does 2 have a left subtree? Which it doesn't. Next, and remember, the next higher priority path that you take is the right subtree. So let's look right child, there's 3, right? So you can kind of see how this this plays out perhaps. So now that we're at 3, it neither has a left nor a right. So now we just start by outputting 3. So I'll make a results text here. Results is 3, right? So that's our first result node, okay? So once we've outputted 3, we kind of bubble back up. So we've taken care of all the children of node 2. So now we output 2, right? And we bubble back up again. Let me drag this sucker out. Whoopsies. There we go. All right. So we're taking care of 2. Now we go back up to 1. But remember, 1, initially we went down a left subtree of 1, right? That's how we got to 2 and then 3. But since now we're back at 1, notice that 1 has a right subtree, right? So in the spirit of this order here, we want to visit the right subtree. So visit 4. And 4 doesn't have a left or right subtree, so we output 4 now. And finally we go back up and we output 1, right? So the result of this is 3, 2, 4, 1, right? It's a little not intuitive, but I think you have to think, because you have to go down like deeper and deeper layers, and it's almost like recursive thinking. But yeah, if this isn't really intuitive to you, take some time to think about it, like draw out some more examples and try to get into like a better mindset, because that's I think that'll help with this question. All right, so now that we've kind of established this definition and example of what post-order traversal is, let's go ahead and I'm gonna clear out this board here and start with a simple example. Get rid of this as well. Right, so let's start off with a simple example. And again, whenever you go through these LeetCode questions, I would recommend first starting off with a simple example. Like maybe 1 node is a little too simple. Maybe in this case we can use 2 nodes, so like a root and then a left or right child. So let's start off with just a root node and a left child. And this might be obvious, but the reason that you kind of start off simple is because if you jump in too much into far end, into like a too complex of an example, it'll not only be overwhelming, but it'll be confusing as well to kind of process. So if you start somewhere simple, you can kind of get the foundation down of what you're trying to do. That way you can kind of build up your solution instead of, being shown like everything at once and then kind of like getting lost, getting confused, like thinking about all the edge cases maybe a little too early kind of thing. So definitely start off simple if that helps, which it should for most people, I think. All right, so this example, I think I haven't actually used this too much. Oh, here we go. That's the line. Lovely. It's like, how do you draw a line, like a straight line? You just drag it out like that. Cool. So sorry, it's not the perfect arrow, but I think it should suffice. Okay, so basically, let's look at this tree here. It's a simple tree. So this question is similar to the in-order traversal question. Now, if you remember that question, again, it should be linked in the description box below. We start off that question by traversing down the left side of the tree, like going down, keep on going down to nodes until you've hit no node in a tree. So this is somewhat similar because in this case, we're remember going left subtree first, and then right subtree, and then the root. In the in order traversal, that last question that we looked at, it's left subtree, root, and then right subtree, right? So in both these cases, we're going down left first. So maybe we can start doing that because we want to prioritize going down the left subtrees, right? So let's say we write the text down. Oops, go up. All right, so let's just write down the high level approach perhaps, and then we can kind of start coding, or or we can even like inject some pseudocode here if we find that to be the case. Pardon me. So we're gonna traverse down the left side, right? So code-wise, that's maybe I won't go into the details, but just on a high level, what we did was we had a while loop, and then we kept on setting the current node that we're looking at to current node dot left, and then pushing each current node into a stack, because remember, we want to keep track of what we've seen because we're traversing down, so we still want to keep track of what all the nodes that we have yet kind of like perform operations on, right? So in this case, we're going down, starting at root, and then going down left child. So 1, and then 2, and then eventually we're gonna hit none. So maybe I can even like draw this out. I'll make a different shape just to be like super like explicit about what this is. So this is basically like none, right? So it's like there is no child here, but we're drawing out just to be super clear here. Okay, so say you're going down this, traversing down this tree, and then eventually your pointer, let's say you have a pointer called current, right? Current, sometimes you might find me just looking at my computer because sometimes it doesn't record, so I want to make sure that I'm actually recording before like, continuing on. It's happened before where I was recording, where I thought I was recording and I went on for like 20 minutes and like wasn't recording. That's like it's a pretty crappy feeling, but it's good practice. Okay, so it's current node. If we do this traverse down the left side, the current node will be pointing to none, right? And actually, just to be super explicit, so I'm kind of jumping around here. Basically, what this code is, I'll just write it down. So while the pseudocode, while current node exists, we basically want to, let's say, indent 2 spaces here. We are appending the current node to the stack, and also setting current node dot left. That's how we actually traverse, right? So I hope this actually will format this correctly. Okay, kind of. I haven't really figured out how this formatting works, to be honest. Okay. Yeah, hopefully this is, sorry it's not like a perfect format. I'll have to figure out later how to do this, but you know what? Let me do this. Sorry, this is a little ad hoc. This is doing this live, folks. Let's take the notes here, and then I'll do this lovely thing, which I should have done earlier, which is to pull this out, blah blah, and lovely. All right, this is great. That way we can kind of use both at the same time. It moves all the way out here, so you can still see the code. Okay, awesome. This is a little better here. All right, hopefully this is like large enough for you guys to see here. All right, so here's the code, pseudocode, I should say. Right? So eventually, this simple while loop will lead you all the way down here where current node points to none, right? But in this case, so what do we want to do once we've hit the bottom of that barrel, so to speak? Notice I'm using a lot of like non-technical terms, so hopefully this isn't a computer science class. So like, hopefully I can kind of help you guys with like the high level thinking, like approach, but like it's not going to be super detailed or technical because this is not like a research paper or an academic class or anything like that. But so current node points to none, and So what do we want to do at this point, right? So all right, it's great. It points at none, but we still have 2 in the stack, right, at this point. So I think maybe you should think, all right, so we want to probably do something with 2, right? Because we want to go back up to 2. We want to refer back to 2. So one thing we do here is maybe what if we access 2 by looking at the stack, the last element on the stack, right? Because it was the most recently pushed element onto the stack was 2. So let's look at this node. I'm just going to call it node here. Again, I'm looking at this code here. So node is stack -1, which means the last element, which is 2. So I'm just going to comment this is node 2 right here. Node is 2. Let's call it 2. Okay. Right. So what do we want to do at this case? So we have 2. That's all great. But remember, kind of going back to our definition of what post-order traversal is, we see that the left child is none, right? So that's great because we don't need to do anything with it. And we've already checked that it's none by this while loop here, right? So we've kind of handled the left traversal already. Like that's fine now. But now we want to visit the right child of 2, right? In this case, there is no right child. So what do we do? So basically, maybe we can start to introduce some logic here. So if node dot right does not exist, what do we want to do? Well, we want to output 2 into the results list, right? Because we've checked the left child, which we knew was none from that while loop traversal, and we just using this conditional check that does not exist. So in here, in the if node.right does not exist, maybe we want to append or push the node onto the results stack, results list, sorry. So maybe what we can do is, let's say we have a results list. We can take append node.val, right? So we can do that. And so basically that takes care of 2 at that point, right? At this point in the code. So since we've taken care of 2, we can pop it off the stack because we don't want to work. We don't need to save it anymore. We don't need to perform any more operations on it. So what we can do is say stack.pop, and that'll pop off 2. And then stack will now just be, I'll be really explicit here. Stack will be an empty list here. Or sorry, it has 1, remember. But 2 was just recently popped off. Right, okay. So stack is now 1. That's all great. But we still want to somehow go back up, right? So what do we do in this case? If we go back up, how do we go back up here, right? So like in this case, this is where it starts to get a little bit tricky. And again, I'm kind of like thinking this out loud. Like, so we've already popped off 2, and we need to somehow access 1. So what if we set the current node to the most recently added item on a stack? So again, it's going to be current stack. It's going to be stack peak or stack the last element in a stack. In this case, right? So let me really quick just kind of comment this part out. Okay, awesome. So at this point, current node is going to be pointing to 1, right? So you can kind of see like we're starting to like do the same thing over and over again. So there's some kind of loop here probably happening. So like once we reach this part of code, we probably want to like go back up, right? So like what we can do is we probably have some kind of loop here. So I'm just gonna for now just put loop and then put everything inside of here, right? So current node is stack of, so current node points to 1. Now we want to, so if we go back up to this logic, this is where it gets a little bit tricky, because at this point, current node, according to our logic here, we want to traverse down a left side again. But remember, we've already traversed down one's left side. Like we already saw 2 and then so on and so forth. So we don't actually want to do this again, right? So this is maybe not the best approach. Again, I'm doing this live, guys. So like, I'm kind of like taking you through like a real like thought process when it's not as edited. So like, I'm gonna make some mistakes here, but like this is part of like the process of like figuring things out on the fly, which is like what you'll have to do like in basically everything, right? So in this case, this part might not work. So the question is, how can we move this here? All right, because up to this part where we stack.pop, it's fine, right? Because we appended, to be really explicit, so 2 is in a results list, that's fine, all right? And we popped it off, now we're back up to here. So maybe something we can do is, this might work, and again, we're trying this out, is we can, so we've basically seen 2, right? So like, one thing you can do, and this is something that applies to like some LeetCode questions, and especially stacks and queues, is to have a visited table or a visited map. I like to use a map. So what does that mean? That means once you've dealt with one node, like once you perform some operations on it, like for 2, we've already performed some quote unquote operations, and those operations entailed, checking the left side, checking the right side, popping it off, adding it to the results list. Like once you've handled that node, it's like, it's good. We don't want to deal with it anymore, right? So at this point, once you pop it off, so maybe over here, we can add it to some kind of add to a visited map, right? So I'm gonna do it this way. There might be a better way we can do it, and we can like iterate over this on the next video. But what if we had like a visited map? I'm just gonna initialize it up here. And while I'm doing that, let me initialize everything else as well. We have a stack, we have the results, obviously. Okay, that's awesome. So we have this visited map, right? So what we can do is we want to add this node to the map. So what I like to do is, one way of doing this, maybe there's a better way, but for now, let's just go with this way, because the important idea is using a map, because you can access a map quickly given a certain key, right? And you can access it in constant time. Is to add the node's ID. And what do I mean by node? Basically what I just popped off, right? So we popped off 2 in our example here. Add 2, whatever, because each node has a unique identifier. And so we want to avoid collisions, right? So we want to take the ID of the pop node and essentially set it to true, right? So we're adding it to a visited map, right? Okay, so that's great. So now, like at this point in the code, we know that we visited 2. We can easily check this visited map to determine if we visit a node, right? So maybe if we go back up here, remember, so like earlier the problem was we don't want to like go back down the left side again in this while loop, because we've already checked that like initially. So like maybe in this case we can say while current node exists and current node not in visited, right? So it hasn't been visited yet, right? Let me zoom out a little bit so it's a little bit easier to read, or a little easier to see everything on one. Actually, I kind of want to make it big so you guys can kind of see it easily. Oopsies. Okay, let me pull this over. Sorry for interruption. Okay, move this over. All right, so, okay. All right, awesome. So we're checking if the node exists, and importantly, the current node has not been visited yet, right? Because that'll avoid us like going to this infinite loop where you keep on checking 1, 2, none, 1, 2, none, so et cetera, over and over again. So, all right, so this looks like it'll help us handle this case where we've kind of checked 2, we've done all the popping and stuff, and we're now back up to 1, right? So we're going to bypass. So going back to the code. So remember we've gone through this loop once. Now we're going back up here. This conditional fails because current node has been visited. So we skip this loop and we go to here. So at this point, node is going to be 1, right? Because the stack is still just consists of 1, right? So now let's see how this plays out. So if node.write does not exist, which it does not, then we results.append node.val. So okay, so 2, 1 popped stacked pop is stack.pop. So we pop 1 off. It's empty. Awesome. Set visited to true. So now it's going to look like something like ID of 1 or 2 points to true. Whatever this ID is, I'm just going to explicitly write it out just because it's we don't know exactly what the ID is, but it'll look like that. Comment that out, and then we'll enter this part of the loop. So current node is now the last element. So this is going to throw an error just because this is an empty list. So maybe, I know this is not quite cleaned up yet, but maybe what we can do is have an extra check here. So if length of stack is greater than 0, right, then we only access the last element in the stack, right? Okay. But in our case, the stack is empty, right? So it's going to bypass this. And current node, so we're going to go all the way back up. Oh, so remember, we're going to go up to this loop. Yeah, so we need to break out of this loop at some point. So now maybe let's think about what this loop could mean. So similarly to our last in order traversal question, it would make sense that we want to continue doing all these operations while the stack is non-empty, right? Because that means we still have nodes in the stack that we want to perform operations over. So one thing we do is while, this is similar to what we did in the last video, it's greater than 0, and we'll probably want to add this check, and current node is not, I'll just write the Python code for this because it's not too hard, is not none, right? Because now I'm starting to maybe get too much into code, but you can kind of start to see like this is similar again to our last question, right? Because while the stack is not empty and we have a current node to look at, then we want to do all these operations, right? So yeah, so basically let's go back here. So current node, so remember we bypassed this, and then stack at this point is empty, so it's going to break out of this. So from our analysis here, given this simple tree, just 1 and 2, it should work, right? So let's go, yeah, maybe we can go ahead and just like maybe just test this out, let me get rid of this comments. And again, this is like not a true LeetCode like interview session, we'll do that in another video. This is more like analysis. So like in a real LeetCode session, you're not actually able to run code. You should do dry runs, like especially like write things out in comments like we did in that previous example. So while current node is this, so it's not none, and current node not in visited. Stack. Why is this comment not like this? Oh, okay, maybe it's an indentation issue. Okay, sweet. So keep going. Make sure if no right does not exist, AK is not none. Just making sure all the code syntax is looking bueno. Okay, and ultimately once we've finished working with the stack and it's empty, we want to return the results. Makes sense. Okay, so let's maybe run a simple example, the example tree that we have here. which is 1 and 2. So just making sure this tree is not well. Okay, so let's try running this, see if we have any errors, and we can just debug if there are. Oh, great. Empty result. Interesting. Okay. Let's see what happened. So, and it gave us an empty result for some reason. Current, let me see. I'll start from the beginning. So current node set is root, while current node is not none, and current node. So we should try check this. ID current node not invisited. Because remember, we're storing the ID of the node. Stack.append, current node. That makes sense. Current node left. Makes sense. If node.write is not none. Oh, I think this should be is none. Right? Okay. All right, so I can already see, like, you know, obviously this is a simple example. Like, we're only looking at, this is an example where only the nodes only have left children and left subtrees. So in this case, we're not checking the case where it's right. So I'm guessing, like, as we progress on this, there's going to be an else condition here to check for the, what if there is a right child, right? But let's not worry about that for now. Let's worry about this simple question and try to get this figured out so that we know we have a good foundation to start from. So let me run this code again. Here. And again, it is empty. Why is it empty? So if node.write is none, results.append node.val. Interesting. Node.write. Let me think here. Node. Why is it so weird? Why is it empty? Okay, so we can do some debugging here. Let's say, I wonder what node.val is in this case. So we're going to see what node.val is in this line. Nothing printed out. That's strange. So it looks like it's not even hitting this part of the code. Okay. That's helpful, I guess. So why isn't it hitting? Oh, this part maybe. Yeah, definitely this part. It needs to be an or statement, right? Because otherwise, in the beginning, the stack is length 0, so this is going to fail the and conditional. So we need to be an or. Let's try this. Okay, loading out of range. Okay, so it looks like at this point, this indicates that the stack is probably empty at this point for whatever reason. So like a very simple, maybe not the cleanest way of doing this, but that should suffice for now, is to, when we check the length of the stack is 0, then we return results, right? Because at that point, I think probably what's happening is that it's like it goes through the tree. I'm guessing at some point current node is not none. So current node exists. There's an actual node, but the stack is already 0, which is gonna cause it to go into this loop, and then somehow it hits this part. I'm guessing it's when, like, we go back up to 1. But for the purposes of this exercise, let's add this little conditional here and see if this works. Okay, so 2, 1 and 1, not ideal. Okay, we're getting closer. Okay, so let's see what's going on here. All right, so what we can do is let's go ahead and just like retrace our steps here. So just start from the beginning. So current node is 1, right? So current node is 1, or we gotta be patient. Current node is 1. So while current node is not none, which is the case, stack.append. So stack is gonna be 1, and then current node is gonna be 2, right? So let me go back up here, get rid of this because we're now in this part of the loop. blah, blah. Current node is 2. So stack 1, 2, and then current node is now none, right? Because we reached the bottom like of this tree. I'm not going to refer back to this because it's a pretty simple tree. So you can probably maybe just imagine it, if you will. Okay, so now we continue here. If length stack is 0, which is definitely not the case, then, or not then, but we skip that. So we stack node is equal to 2 in this case. If node.right is none, which it is because it's already at the bottom of the tree, results is 2. And then pop the stock. So stack is now just 1. And then we have like visited is like the ID of like 1. I'll use the colon here just for simplicity's sake, and it points to true. If length of stack is greater than 0, which it is, so current node is now set to 1, right? All right, great. So now we're back up to here. Remember, current node is 1. Let's make it really explicit. Current node is 1, so it's definitely not none. So while current node is not none, which is the case, and ID current node not visited, which is not the case. So it's going to bypass, ideally, all of these, like these checks here in the second part iteration of the loop. All right, so it bypasses and goes length of stack is 0, which is not. Remember, stack is still containing 1. And then the node is the peak of the stack, which is the last element. So it's the node is 1. And if node.right is none, right, 1 doesn't have a right child, so this is true. We do results.append node.val. So now we append 1, awesome. And we get rid of the element from the stack. And now the stack is empty. All right. So now we popped off. Wait, did I? Oh, okay, this should be ID 2. Sorry. Yeah. So sorry about that. Okay. Anyways, so we popped off just popped off 1. So now we add ID 1, and that should be true. Okay. And length of stack is greater than 0, which is not. And now we go back up here. So remember, while length of stack is greater than 0, which does not satisfy this case, but current node does exist, I believe. And what is current node? I actually don't. We need to kind of retrace our steps. Let's go back a little bit to the previous iteration of the loop. Current node might still be just 1 because we never set it. Remember? Yeah, I don't think we ever like set it. An ID. Actually, no, I see a bug. Yeah, there's definitely a bug here. So like what we did was, remember earlier when I said ID 2 is true? Like, all right, we got to retrace our steps. Sorry guys, let's retrace our step. Again, doing this live. I think going back to the first iteration of the loop. So current node is, let's go back up here. So once we've essentially popped off 2, right? We popped off 2, and stack is still full of 1. Sorry, so we've added 2 to results, but stack still has 1. Yeah, so what we popped off was actually 2. Yeah. Right? Wait, node.stack. Sorry. So added 2 to results. Yeah, we pop off. Okay, yeah. So we popped. 2 is what we finished like looking at, and so we popped it off, and now we set it as visited. Okay, so we're going back up here. So current node is 1. That's all great. So now we're here. So while current node is not none, and ID of current node not invisited, which is both of these are true. So actually we're gonna start going down here again, right? So like I think this is where the issue is. So stack is now gonna contain 1 and 1, right? Because 1's already in there, right? But like our current node is set as 1. So like I think there's probably an issue with like how we set the current node perhaps. So let me think about how we can deal with this. All right, so current node is, link stack current node is 1. Because we've already popped off 2, that's fine. We just don't want, basically what I'm thinking is we don't want to traverse down the left side of 1 again, because that's what we did in the first place. So how can we like not do that? How can we avoid like, how do we bypass that part, like a traversing down, right? So like current node is 1, because like basically this is like kind of where we start off, right? So in the very beginning of code, current node was pointing to root, and root is just the 1 node, right? And but like once we run through like all this code here, like goes 1, 2, checks left, right, child, all that, somehow end up back here. We don't want that to happen, right? So how do we avoid that? So in this case, let me think. Sorry, guys. All right, I think I might have an idea of what to do. So, so again, our problem is that once we've gone through this loop once we've gone down 1, 2, and then we've checked left child and right child, we pop that off, add to the results array. Once we're back up to 1, we are traversing down again, which we don't want. So I think maybe, so to avoid doing that, one thing we could do is in this conditional, instead of having the visited check in the actual conditional, we might be able to have it check the child in inside the while loop. So in this case, right? Because in this case we know that 2 has been visited. So what if we say, what if the left child of the node is visited? Because if that's the case, we don't want to travel down the left side, right? It makes sense, right? Like, so we're looking at 1. All right, so it's like, all right, let's try traveling down the left side. So look at 2. Oh, but we've already traveled down the left side. So we can just check the left node of this 1 node, right? And that should prevent us from actually performing that traversal down the left side. There might be a cleaner way of doing it, but again, like for purposes of this exercise, let's try it like this. So if ID current node of the left child is not invisited, let me get rid of all this dry run here that we were doing earlier. Just to kind of make things a little cleaner. All right. So if the left child of the current node has not been visited, then we only visited, right? Else we could probably do like a break here. Yeah, because in this case, like, it doesn't really matter too much, because if we did not have the break, because it's only like 1 node. But like, imagine this was like a tree of like depth, like it had like a million layer, it had a million levels, right? A depth of 1 million or something like that could, start to cause some problems. Like that'd be a little that would exaggerate the inefficiency. So like let's add a break here. So like if it's been visited, then we just break out of here, right? Okay. So maybe this will, I have a hunch that this will kind of improve our situation. So it'll prevent us from kind of double checking that 1, as evidenced by this buggy code that we just ran. So let me run this again. Let's try this. All right, awesome, cool. So let's, so this works for at least for the simple the left child case where a tree only has left children. What about the case? Let's do one more. Let's do 1, 2, and 3, like a little bigger tree. Null 3. There we go. All right, let's try like a tree of level depth 3. Let's see if this gives us the right output. Nice. All right, cool. So yeah, it works for like this one-sided tree, but let's see. Let's start to make it a little more interesting, right? So like, what happens? And I'll remove the none because this is I think you guys kind of get the idea of that explicitly. We don't need explicit pointing to a non-existent node. So like, what happens if we have? Let me maybe add it here, right? What happens if we have a right child, right? This is where it starts to get a little more interesting. But I think we have the foundation down for our algorithm here. Because you can imagine that the left child, or sorry, if it had a right child, it's similar, right? Like, it's just another node, right? Like, and we probably talked about this a little in the last video. Like, it's sometimes you might think, oh, like this connects to this, 1 connects to 2, connects to 3, like, holy cow. But like, if you just isolate 3, like forget like 1 and 2 even exist, right? Just look at 3. Just look at 3. What is it? It's just like 3. You can just imagine like it's like the beginning root of a tree in itself, like in this case, what they call it, like a subtree, right? So it's like not any more different from 1 and 2. It is connected to 1 and 2, but it's like on its own. And if it had like any other like branches flowing below it, it would just be like a similar tree, just like the similar root of a tree, just like the 1 is the root of this tree, right? So with that kind of thinking, what if, so going back to the code, let me get rid of this console here. Okay, so we kind of have like, let me zoom out a little bit, right? So remember earlier we have a check for if the node.write does not exist. But what if it does exist? Right? Else, speed really quick, node.write exists, right? Well, in this case, what do you think would happen? That means like we have a right node that we need to look at. So we can probably just pop this onto the stack because it's something that we need to further explore, right? So what if we just pop this onto the stack? Stack.append node.write, right? Because then once we pop it on the stack, we're now saying, okay, now we need to start looking at it. So we go through the rest of the code and we'll eventually end up back up here. And we're basically ending up where we started with 1, right? Which is like I mentioned earlier, because 3 is like a subtree in itself. Like we want to do the exact same thing basically we did with 1 as with 3. So this kind of like gives us that ability, right? So I think this will work actually. So let me try running this. 1, 2, 3. Actually, this is a bit of a different example, but I think it's the same. It's actually just to be consistent. Let me make this null, another null, I believe. Yeah. All right. So let's go ahead and run this. This might time out because usually when it runs for this long, there's some kind of infinite loop going on. All right, so time latency. Okay, so let's like take a closer look, see what happened here. Oops, move my face out of the way. Awesome. Okay, so else node.write exists. We append node.write to the stack. Okay, is that all we need to do? Because say we append to the stack, and let's say here, let's see, we've appended it. if length stack is greater than 0, which it is, then current node is, let me make this smaller so I can click into both. Current node is going to be pointing to 3 in this case. I know I'm skipping ahead a little bit, like I didn't really fill out all the values in the variables earlier, but just starting off from 3, so current node is 3, and then while current node is not none, if the left child not visited, ID not visited. So the current node in this case is 3. Current node at 3 is none. And it should not be. I wonder if this actually like ID of none is actually a thing. If current node, maybe this, because current node. I think it should be fine actually. Or yeah, there might be an issue because like. So basically here current node is 3, right? It's all fine and dandy. So but if ID of current node dot left is not visited, but the left node of the left child of 3 is none. So ID of none not visited, which is going to be the case because we never stored the ID of none in the visited map. So maybe we can do a check here if current node dot left is not none. And okay, because that'll bypass the none part. Okay, that's great. Okay, let's try running this. Let's see if this breaks this out of the loop. Okay, it's a little better, but we're still seeing some issues here, obviously. Okay. Get rid of this and make it a little smaller. Yeah, so we see 3. Let me go back here. All right, folks. So I'd take a little bit like a 5-10 minute break just to kind of think this. And to be honest, this is definitely a bit of a tricky question. The recursive solution is pretty easy and trivial. It's like a couple lines of code compared to this. I'm sure there's definitely cleaner way of approaching this question, but it's not very intuitive, right? So like this gives you kind of like a real life, honest like view into like how the thinking process works, like how sometimes you might fail, but like you kind of have to just, you kind of just have to like, take a step back and just like think things through and just like try to regain your patience, right? Because sometimes this might get a little frustrating. You're not like building a UI that you can actually see. It's like not as tangible. It's a little more abstract. Some people like it. Some people will find it a little more challenging, but yeah, so I think the issue might be that I'm a little concerned about this check because this is getting a little not convoluted, but it's getting a little hefty here. Like we have to like, like I said, the ID of none, taking the ID of none and storing it in visited, like that never really, like that doesn't really make that much sense. You want to take an ID of an existing node, right? So like I think I'm gonna try to get rid of this part. Let's try to simplify this to just ID of current node. And so because we're doing this, we'll probably have to adjust the rest of the code, but that's okay. So like, let's make this a little easier. So if ID of the current node in visited, let's actually make this logic reverse so that we can clean up this else statement here. Yeah, so sometimes it helps to take a step back, try to clean things up, because at the end of the day, a lot of LeetCode questions, from what I've experienced, have short, concise answers, right? It's like, obviously it's up to you to kind of find that, but like if you notice that your code is getting a little too crazy, which it is in this case, like it's a sign that maybe you're overthinking it. Maybe you need to take a step back and kind of revisit your approach. Yeah. So okay. So let's clean this part up. So now clean this part up. Now let's see. Let me move my face down. Okay, let's go through this. If length of stack is 0, return results. That's fine. I'm also a little concerned about this current node part here, this node part here. So if you remember in our previous video, we kind of continually set the current node. I'm a little worried about like using extra nodes, extra variables here. So let's set this current node. Let's just rename this node to current node. So like we're basically reusing the variable up here in place of like a new local variable, right? So let's replace every reference to node to current node. Okay, so current node is the last element in stack. If current node dot write is none, nothing. That means nothing exists. That means we can pop off the value. Let's pop it off first, actually. Again, this is just kind of like walking through like an intuitive understanding of things. So we pop it off, right? And then I don't think this will really change it too much, though, to be honest. But yeah, so pop it off and then take the value, and then we'll store the ID of the visited visited node here that we just popped off. Else, if it exists, that we want to do something. So we want to add current node dot write to the stack here. So like in this case, current node dot write would be 3. So we're adding 3 to the stack here. So I'm trying to think if that does that make sense, because okay, current node dot 3, and then down here, if length of stack is greater than 0, if there's an element in the stack, at least one element in the stack, then we set current node to that element. So current node means we're looking at that element now. Okay. I can see another issue here, because like if current node is 3, then once we go up back to the top of the loop, remember, so we're traversing down the left side of the root or a current node. But by the way we designed this, we're also pushing the root node that we start at. So stack down here contains 3, right? Because we push it on here. But once we go back to the top of the loop that traverses the left subtree, it'll again push 3 onto it. So okay, so we're pushing 3 twice. So that's kind of a problem. So how do we deal with that issue? Like we don't want to push it twice. Let me think. Yeah, because remember earlier we had to check for if ID current node and visited. If it's visited, then we break out of it. Because remember, earlier we had an issue with like, 1 and 2. Because remember, we were when 3 was not there, so I'll kind of move 3 down. Let me actually hide it with my video. So remember when it was just 1 and 2, like when current node, we're back up in this part of loop again. When current node was 1, we had an issue with like visiting 2, like going down, traversing down this list again, or sorry, this tree again. But I think this is fine because I guess we changed the logic a little bit because yeah, let me think, see if this works, because so if ID current, let's just go back to a simple case of 1 and 2, right? Let's see what happens here. 2 on 1. Okay. So I think what happened, so it looks like we are actually like, oh no, because we haven't just this. So this is where we're like kind of adding that extra 1. Because like remember, just like with the 3 example that we just had with this full tree, like we're adding the 1. So maybe like earlier when we were thinking about the issue with 1 and 2, maybe it wasn't exactly what we're thinking. Maybe we need a different approach for that. So I'm thinking, so maybe it's the way we set current node. So remember, current node is, oh, this is kind of tricky, dude. Current node is, current node has been visited, but we've only added the pop nodes. So again, I'm looking at only the 1 and 2 case here, like because I'm looking at this tree. We're only looking at this tree for now. We're kind of revisiting this again. We're trying to improve our initial code. Is what we're trying to do. So lengths. So remember, we don't really have to worry about this part yet because this tree only has left children. The nodes of the tree only have left children. So how do we? Maybe. Maybe we can. Man, I'm really not sure. I'm thinking. I'm like thinking in circles. Current node is not none. Current node. Because we don't want to add it twice, right? So maybe we're adding it to the stack down here a little too early. No, because it's already there. Maybe we pop it off? But we only want to pop it off when we don't want to visit it anymore. And like, what if 1 had, like in this case, so we're looking at this 1 and 2 tree. What if 1 had a right child? Like, we don't want to pop it off too early, you know? So, okay, so I have an idea. Maybe, because the issue is if we store, if current node is pointing to 1 in this example here, to bypass this while loop check here, maybe one thing we do is instead of setting it to just 1, we're going to set it to the left child, right? That way, yes, that way we're bypassing this traversal. And also here, we are resetting the current node to 1, right? Because remember, the stack already contains 1 and only contains 1. So current node is going to be set to 1 here after it bypasses this left traversal check. So let me try this. Okay, awesome. So that seems to work. Let me try another case here, like the longer one from earlier. Tricky question. Awesome. Okay, so we're making some headway here. Awesome. All right, so yeah, we just had to kind of revisit our initial approach. And this happens sometimes when you start off with a simple approach, and then you kind of gradually make it more complicated. like we did here. We went from like this tree with these two nodes to this tree, and then we kind of discovered our initial approach. In general, fundamentally, it was the foundation was there, but the details were missing, and we had to kind of fix some bugs, correct some details, which is fine. Like that's like the process of like improvement and like iterating and kind of refining your solution as you find more use cases or cover more use cases. So okay, so now let's go back to our little more complicated example, which is when a tree has a right child somewhere, like this case. Okay, so I'm curious what happens if I just run this, but let's not jump ahead too fast. Let's try to analyze this a little bit more. So okay, so basically our previous example, simpler example, covered this case. So now we're kind of introducing this conditional. Like our code is now going to start to hit this part of the logic, which is to append if the current node.write exists. So like say we've hit, we are looking at 2. I got current node is 2, and we notice that there is a right child of 2. Then what do we do? Well, in that case, we want to. Okay, so we probably. I see. So remember, like this is going back to this traversal check. So this traversal check is maybe, I don't want to say not right because it's been like working, especially on our previous question, but maybe we really need to kind of hone in and think about what this does. Like, so it starts with the current node and it assumes that the current node is not in the stack. So it's going to add that current node to the stack. So down here, if we are pushing current node.write onto the stack, doesn't it stand to reason, and as we've seen before, up here, it's going to push it onto the stack again. So in this case, maybe we just want to set, instead of pushing it on the stack, maybe we want to just set current node is equal to current node.write. Okay. So in that case, once we hit this part of the code, current node is now 3, right? And once we go back up here, it'll visit 3 and then push it on a stack. So in that case, it's gonna take care of the stack issue, like not down here in the code. Like this is not where we want it because this will kind of duplicate that node in the stack. Okay, so push it on the stack. If length, sorry, not push it on the stack, but set it. But we have an issue here. So if length stack greater than 0, current node. Okay, so is the peak value, the last value in a stack, the left child. So like in this case, I think this was a remnant, if you remember, of what was this remnant of? Let me check. Was it up here? I'm trying to remember. So if current node.write is none, okay, yeah, it was a remnant of this up here, because if you remember, this is right after checking that a certain node doesn't have a right child. And if it doesn't have a right child, that means we want to store that node's value in the results and set the current node to that node that we're going to pop off the left child of that node that we're going to pop off, because then we bypass this traversal check, if you remember earlier. So let's add this up here. Okay. Okay, it's starting to look a little better here. Or at least it makes more sense. Again, this is like not refined code. We'll do that in the next video. This is kind of like a dirty way of doing things, but I think time complexity wise and efficiency wise, it's similar to like the more like refined solution. Okay, so if length that's greater than 0, set current node. Okay, that's great. Let's try running this, see if we can debug this. Like we're hitting out an infinite loop somewhere. Node dot write. See if I'm missing anything. Time limit exceeded. Okay. Else current node dot write. I wonder if so remember earlier we were like revisiting nodes that we had already seen, and hence that kind of caused us to introduce this like visited map. I wonder if the same thing is happening again here somewhere. So let's go back to the graph. I'm a very visual person, so it helps like kind of look through things. So, okay. If we set current node dot write. I'm trying to think of just maybe a case where current node dot write has been visited already, but I'm trying to think. Move this over here. Oops. That was my earlier implementation. Okay. Oh, getting tired. Let's see here. Node dot write is none else. Maybe it helps to walk through this one more time. I know it's hard to like walk through things because you see a lot of repeat stuff, but like let's try that. So let's start off with 1. You know, all right. So here we go. Current node is 1. If ID current node is new, it's not. So stack is 1, and then current node is now 2. Okay. And length the stack is 0 is not. So current node is now. Oh, sorry. So I'm jumping the gun. So like we have to like go back up to here. Current node is 2. Going back up here. Now it's 2. Now I pen 2. Current node is now none. Now we finally break out of this. Jump down to here. Current node is the peak value, which is 2. That's great. If current node dot write is none, which is not. Jump down to here. Current node is 3. Awesome. So jump up to here. So current node is 3. If ID current node and visited, which has not been visited. Append current node, which is 3. That's awesome. Now current node is current node dot left, so it's like 3 dot left, which is none. That's fine. And then blah blah blah. Continue. Current node is 3. Current node dot 3. Current node dot write is none, which is a case. Stack dot pop. So now stack is just 1 and 2, and results is now 3. And then visited contains just like I'll just say 3 just to keep things simple, instead of ID of 3. 3 is true. Okay. If length is stack greater than 0, current node is, excuse me, current node is the left child of 2, which is none. Interesting. Which is none. Okay. So let's go back. Now we go back up to current. Well, current node is not none. Okay. So current node is now stack -1. Last element stack, which is from down here, is 2. Code current node dot right is none. So we're starting to see. Okay, I starting to see why we're repeating this, because because here like we're checking current node dot right. We're checking the right child of 3 again. Oh, sorry, the right child of 2 again, which is 3. So once we like done all our operations, we'll go down 1, 2 to 3, and it kind of bubbles back up to 2, just like we kind of saw, and then it'll check 2 dot right again. But like we've already visited 2, so I think here what we want to do is perhaps our current node dot right is none. Wait, sorry. No, it's not right, because current node dot right is not none. So sorry. Scratch what I said. So we're actually entering this part of the code, but maybe the same thing applies. Let's see. So current node is 2 dot right, which is 3. Okay, so yeah. So similarly, we're kind of seeing a repeat of what we just saw. So I think this is where the infinite loop starts here. So interesting. Current node is 3. If and visited break. Actually, it does break out of this, but we see that current node is, oh, so it resets to 2 again. Okay, interesting. Yeah, so like we are like resetting current node to 3. Maybe if we added because we've already seen 3, so we don't want to see 3 again, right? So okay, so we want to say current node dot right not invisited. Current node dot right not invisited. This is so much easier done recursively. Yeah. So yeah, I feel like this solution is a little bit hacky, to be honest. Like it's obviously very hacky. Like it's not ideal. Because like there's no like consistent meaning for like what current node is. You know what I'm saying? So when current node is 2, say current node. I know it's getting really like messy. This is why dry runs are also like very much a pain in the butt. Where you need like some time. You need some time and practice for sure doing dry runs, because like it's so easy to get confused about like all the text going on. Yeah. So like let's assume current node is 2, right? And let's assume that we've already visited 3. So we're gonna bypass this. We're gonna go back up here. If current node and visited, ID current node and visited, break. Have we visited? Did we already see 2? We already saw 3, but oh, maybe we want to do this. Maybe we want to say, and it's already been visited, right? So like instead of here, because we want to somehow pop 2 off because we've already seen 3. So if current node.write is none, current node.write is none, or current node.write has been visited, node.write in visited, id current node.write in visited, right? Then we pop it off, right? Because we're at 2, and say we've already visited 3, we've already added that to the results array. And then we add 3 to the visited map. Now we go back to 2, but 2 is now checking current node.write again. It's not none, but also it's not none, but its write child has been visited before. So that should signal to us that we now want to like pop this off the stack, 2 off the stack. So we pop it off and then proceed as we do. So let me try this. Oh, this is not Go. This is Python. Okay, so this works. Does this actually work? Hallelujah. This works. Let's try some more funky examples. 3, null, add a few more nulls, why not? Let's see what this tree looks like. Something like that. Let's run this. Yeah, let's try submitting this. All right. Well, not a good sign that I'm a little bit surprised by it, but like I said, this is a bit of a, tricky question. I'll be honest with you guys. Like this is obviously one of my first videos. Like I'm just starting to post videos, and I kind of gave myself, I do work a full-time job, and so I don't have as much time to spend on these videos as I'd like to. So I kind of time box myself. So like, I'm sorry if this is like not a perfectly fleshed out video, but hopefully, like I said, like this is not perfect, but it gives you like a real life insight into like kind of like the struggle and the, sometimes the frustration of going through those problems. Right? Like things don't go perfectly. I'm not a genius. I'm just trying my best here to kind of go through my thought process, explain how I think it works. And maybe like from my thought process, you can kind of glean ideas or like kind of really get your mindset into mine, and hopefully you can kind of extrapolate some things that I see. Let me move this over here. But yeah, this is a code. This is a dirty version. This is a dirty implementation. And quickly we can talk about like the runtime analysis here. So runtime analysis, we are visiting each node, right? Because obviously we have to visit each node because we need to push each node onto the results list. So in terms of runtime, we're not visiting each node like exponential amount of times relative to like the size of a node. Remember, like for a nested for loop, for each n elements, you visit that element another n times, right? So it's like becomes effectively n squared time for a double for loop algorithm. In this case, we're visiting each we might visit each node, I think at most 2 times, I think, but it's a constant number. So in this case, runtime is going to be O of n, right? Where n is the number of nodes, right? So in terms of space, though, space is a little more interesting because, well, actually, maybe it's not that surprising because the biggest thing is this visited map, right? So we want to know if we visited a node, and by that definition, that means we've included all nodes into this visited map. So in this case, we've stored n nodes into this map. So in this case, space is also of n. We do use a stack, and if you can think about it pictorially, like a stack, we kind of we're adding stacks along the depth of the tree. Remember, like, because we kind of go through the depth, and then go visit the left, visit the right. But as we visit each, like, say we visit the right, we might pop off some nodes. So like at any given point, it's never gonna. I should say this, never gonna be like the entire tree, unless it's like the tree just one straight left tree down, like left subtree, like just only left children down. In that case, the space could be O of n for the stack. But I think in general, like for most cases, like an average, I guess you could say, the stack is going to take up the number of layers or the height of the tree. So basically, the bottleneck in terms of space complexity is the visited map. So that's why space is O of n. And yeah. And all right, so this is my first approach at this question. For our next video, let's well, I'm not sure if it's for our next video, but for our next LeetCode video, let's go over like a cleaner implementation, because this is a very interesting question. And again, the recursive solution is quite trivial. It's like so much easier, because like this is one of those questions where it's just easier to think about it, recursively, because as you can see here, like you're doing a lot of same things over and over again in like a loop, right? And that's a sign that maybe you can do this recursively. So let's do that in another video. And yeah, thanks for hanging out here. This is a good real life like kind of struggle in action, and so I hope that you can kind of at least if you at least learn anything, then I'll be happy about that. And yeah, I will see you guys next time.